atoms in the universe are almost all hydrogen and helium. Other than hydrogen and helium, the most abundant single element is iron. Iron is the configuration of protons and neutrons that's the most stable. Iron is the most stable element in the universe because if you take heavier elements and break them down into iron, energy will be released by fission. The same is true if you fuse lighter elements to heavier element. Explosive nucleosynthesis is required to make all of the elements heavier than iron. Heavier elements like gold and uranium are not created in the center of stars like the lighter elements. Instead, they're only created when a star explodes in a supernova. In some supernovae, the outer shell of the star is exploded off and the protons and electrons turn into neutrons and electron neutrinos. And they collapse down into a neutron star. If the Earth were collapsed down to the size of a ping pong ball, it would become a black hole, but it would not change the moon's orbit. Black holes can only be measured by their mass, their electric charge, and their speed of rotation. The universe is less than 5% atomic matter. There's over 5 times as much dark matter as atomic matter, but most of the universe is dark energy, using the equation E equals mc squared. Early in the universe's history, it was almost all radiation. Eventually, the universe will be almost all dark energy. Dark matter and dark energy are outside of the standard model of physics. Dark matter and dark energy do not emit or scatter light. Dark matter does not form atoms or molecules like atomic matter. Dark matter does not exert pressure or respond to pressure. Dark matter could clump together earlier after the Big Bang than ordinary matter because it was not affected by the photons. Dark matter's gravity brought ordinary matter together. Without dark matter, ordinary matter would be spread out into a lifeless gruel. Even now, dark matter guides the movement of matter in the universe. General relativity says that empty space can have energy. In general relativity, the cosmological constant is the energy present in empty space. Dark energy is probably a tiny residual energy associated with space itself. Dark energy is sometimes called vacuum energy. Dark energy is very slight, only 5 hydrogen atomic masses per cubic meter, but totaling over 70% of everything. Dark energy is smooth tension. Dark energy density doesn't change as the universe expands. As the universe expands, the total dark energy increases and the total radiation energy decreases. The cosmological coincidence is that dark energy became dominant in the universe shortly after stars and galaxies formed. Dark energy is too strong now to allow larger groupings of galaxies to form. Dark energy will continue to become stronger and stronger as it continues to accelerate the expansion of the universe. The larger the universe gets, the more empty space there is, which in turn creates more dark energy. The Hubble constant of how fast the universe is expanding is about 22 kilometers per second per million light years, with about a 7% uncertainty. Nothing can cross space faster than the speed of light, but space itself can expand faster than the speed of light. The sphere surrounding a point where space itself exceeds the speed of light away from that point is called the Hubble sphere. Nothing from outside of the Hubble sphere can ever reach the point in the middle of the Hubble sphere again because nothing can move across that space faster than the speed of light. Galaxies form clusters of various sizes. Individual galaxies within galactic clusters are not moving away from one another, because they're close enough that their gravity keeps them together. It is the galactic clusters that are moving away from the other galactic clusters. The Milky Way galaxy is part of a cluster of galaxies called the local group, about 36 galaxies. In about 100 billion years, all of the stars in the universe beyond our local group will be outside of the Hubble sphere. After about 100 billion years, no light from anything in the universe outside of our local group of galaxies will ever reach us again.